guys, it's IDW, and today we're going to be talking about some of the logic in my GPU CPU that I haven't been over yet. Most specifically predication, because you already probably know what bitwise functions are. So let's deal with bitwise functions quickly then. A bitwise function is an operation where you take each bit of the two operands and do a logical function between them. So for example, if I was to do a bitwise AND between numbers 1, 1 and 0, 1, the result would be 0, 1. The first bit is the first bit of the first number ANDed with the first bit of the second number. So it would be 1 and 0, which is 0. And the second bit is the second bit of the first number ANDed with the second bit of the second number, or 1 and 1, which is 1. There are two really efficient ways that you can implement bitwise functions: CISC and programmed logic arrays, or PLA for short. We're going to be using a RISC computer, so we're going to have to go with the PLA approach. A programmed logic array is a circuit that can be modified to act like any logic gate depending on the controls wires going into it. And by a logic gate, I mean a bitwise logic gate, meaning that each pair of operands would be sent into an individual logic gate. If you disable the carry of an adder, you can effectively make it into a PLA, because without interactions between bits that the carries create, you can make each bit into an individual logic gate. To modify the type of gate the PLA is making, we can use De Morgan's theorem, which essentially states that you can make any logic gate into any other through some pattern of inverting outputs and inputs. There are some important exceptions to this rule that we will go over when we actually make our adder into a PLA, but for now, understand that we can make our adder into a PLA if we add some input inverters and an output inverter to the ALU. Input inverters we already have because we needed them to do subtraction. So we already have circuits that invert the inputs, but we can do something slick for the output. The second XOR in the adder has no use during bitwise functions since there are no carries to XOR the outputs with. So if we send 1 into all of the carries, you can use the second XOR as an output inverter without adding any additional circuits. So to make a programmed logic array, we only need to prevent the adder from carrying and add a function that sends all the 1s into all of the carries. But let's now get into the interesting part, which is predication. There is absolutely no way that the device we are making could do conditional branching, at least without slowing it down, which normally wouldn't be an issue, but we can't do that because of the pipelining design that we are using. It would alter the number of cores that the CPU has. We need to find some way of getting the effects of branching quicker. There are two really effective ways that you can do this. Interrupt, which is where the computer guesses where it's going to branch to, and corrects itself if it guesses wrong. And the other solution, which we will be implementing, is predication. The first thing you need to understand about predication is what a status bit is. A status bit is something that tells you information about the computation an ALU is currently doing. For example, was there a carryout? These status bits are usually used as conditions for branching, but not when you implement predication. The idea behind predication is that rather than using status bits to branch, you treat them as data and store them in memory. And then you use them in functions that give the desired results for either way the program could go instead of branching. Incidentally, a predicate is a fancy name for a formula that implements predication. For example, let's say that you're making a program that rounds a number up to the nearest 2's bit. Usually you would do that by shifting a copy of the number to the right so that the least significant bit underflows, and then branch to an increment instruction depending on the status bit of the underflow. But a predicate to the problem would be to add the saved status bit to the number itself. Because if the least significant bit was on, it will add 1 to the number, and if it's off, it will do nothing to it. But it's not this easy to come up with predicates for every single problem for branching. So let's take another problem, taking the absolute value of a number. Now this task is much harder, we not only have to increment the number, but we also have to invert the number depending on whether or not one bit is on. If we did a bitwise XOR with the data, we could invert each bit depending on the Boolean. But you would need to do that to every single bit to invert the entire number. Well, it turns out that there is a one instruction way that you can turn a 1-bit Boolean into the same Boolean repeated over on every bit. And that instruction is actually 2's complement negation, since it makes a 0 back into 0 and 1 into -1. And -1 in 2's complement is all 1's, which is exactly what we want. 1. So the Boolean in its all 1's form that we use for the bitwise function is what we call a bitmask. We're going to be using them a lot more when we begin to program this thing, and they will be the main thing that we're going to be using bitwise functions for in the first place, but we're going to talk about that another time. So I hope you guys have enjoyed, and I'll see you guys next time.